Hello again, everyone. Welcome to the practice session for Unit 7. My name is Shuang. In this session, we're going to practice forward model run and data assimilation using our framework. We will try to review some concepts and techniques while we do the practice. Thanks to the Spruce project again, we're using their on-site data as an example to show the possible studies you could conduct by using our data assimilation framework. Here is a list of data used in today and tomorrow's practice session. And now let's get on to practice 1, learn to use our framework for forward run. In the next few slides, we will show you some reference answers to the questions in practice 1. This is the figures I made for the default run. We can see we're showing the leaf pool changes throughout the year from 2011 to 2016. And next we're showing the wood pool changes and then the root pool changes. We also plotted GPP, NEE, and ER and other carbon fluxes for your reference. The red dots here is showing the observation data. The observation data file, you can find them from the input folder on the in the offline package. When we decrease and increase VC max value by 30%, we can see there is a dramatic change in GPP and also autotrophic respiration. A decrease in VC max value dramatically decreased GPP. Similarly, when we change the value of specific leaf area by 30%, we can see a decreased value can lead to a decreased GPP and also the autotrophic respiration. However, we don't see much changes in the carbon pools, which is shown here, the leaf pool, wood pool, and root pool. There's no changes by changing the SLA value. From these comparisons, we draw a conclusion that VC max and the SLA have similar effect on model outputs. And then when we tune the parameter value, the turnover time of leaf pool, we can see, although there's no big changes in the GPP flux or the NEE flux, we can see the steady state of the leaf pool have changed dramatically. In the first subfigure, the steady state of leaf pool is about 350 shown on the figure, and then when we increase the turnover time of leaf pool, we can see the steady state of leaf pool carbon content is as large as about 450 gram carbon per square meter. If we tune the red value for the turnover time of root pool by 30%, we see it also changed the steady state for the root carbon pool. And we draw the conclusion that turnover time can affect the steady state of carbon biomass. Although not shown here, but if you have also plotted the result by changing some other parameters, for example, the maximum leaf growth rate, you may find out that the model output are insensitive to the changes of these parameters. To sum up the conclusions from practice 1, we see that certain output variables are sensitive to the change of certain parameter values. And we learned that different combinations of parameter values can generate the same output variables. That means sometimes we might get this right answer but from a wrong reason. An example is the value of turnover time of leaf carbon pool, SLA, and VCmax are all responsible to the magnitude and pattern of leaf carbon pool and GPP. Different models or different parameter values of the same model may fit data equally well without the ability to distinguish which models or parameter values are better than others. In another way, a given end state can be reached by many potential means. Equifinality is an issue for both manual tuning method and also data model fusion. However, manually tuning the parameter values can be tricky and self-intuitive, but data simulation is unbiased. It will look at all the parameters and prior knowledge at the same time with millions of iterations and given probability distribution for uncertainty analysis. Practice number 2. Learn to use our framework for data simulation. Let's review a little bit on the concept of data model fusion. Here are the 3 basic ingredients for data simulation: optimization, model, and observation data. It is a super powerful tool widely used in different research topics, such as numerical weather prediction, atmospheric chemistry, and also the land ecosystem, and then many other different areas. In the broad modeling world, data assimilation is generally used to quantify the variables driving that system by using the observations. Within a physical system, the priority of using data assimilation is to reduce the uncertainty of initial state, while for land models, because the ecological processes are heterogeneous in space and time, so in the land ecosystem modeling world, reducing the uncertainty from parameter variability is the top priority by doing data model fusion. In its mathematical form, data assimilation seeks to make a best guess with the existing prior knowledge, which is on the right side of the equation. Let's review the basic components in the data assimilation framework. Prior knowledge, labeled in blue, it includes the process-based mechanism within the model structure and a possible range of parameter values based on empirical data. And finally, observations such as net ecosystem carbon exchange, methane emission, and above-ground biomass, etc. The first step in the Bayesian analysis is to propose a new parameter value based on the existing samples. For the first iteration, the starting point is usually a random value within the prior range. After a new set of parameter values are generated, we use them to run the model once and calculate the mismatch between model and observations. If the mismatch is larger than the last run, there is a big chance that the proposed parameter values will be rejected. While if the mismatch is smaller than the last round, the proposed parameter set will be accepted and recorded. The ultimate goal of data assimilation is to find a global minimum mismatch between the modeled and measured value. Without using data assimilation, when we manually tune the parameters, model might be able to find a point pretty close to the local mean, but it is hard to get to the global minimum mismatch without millions of times of repeated run like data simulation would do for you. After about 100,000 times of iterations, we will probably get a stable posterior distribution, and that would be the data constrained posterior parameter distribution. There are many Bayesian algorithms used in carbon model data simulations. The one that was used in our data model fusion framework is highlighted in purple. If you are interested in more algorithms, we recommend you to check out this paper listed at the bottom. Here, I want to show you how these steps were coded in our framework. The first equation is the simplest form of generating a new set of parameter values. The second equation highlights how the mismatch was computed within the cost function. Remember that both the mean and variation of your observational data are important. A larger standard deviation refers to a lower confidence in your observation mean, and thus the weight of this mismatch will be small in your final cost function. The third equation is the criteria set to decide to accept the proposed parameter values or not. This is the source code used in our data model fusion framework. Again, I want to show you the workflow of data model fusion framework and help you go through the different steps. Although you don't have to look at the source code at all in order to run data model fusion, let's go over a little bit the basic flow of data assimilation. In the getObs subroutine, we read in observation data, mean and standard deviation. And after that, a new parameter set is generated. Then you run the model, calculate the mismatch, accept or reject the new parameter sets, and then our data model fusion framework will save all the accepted parameter sets and then randomly save 500 sets of model output generated by the accepted parameter sets. After you get a posterior distribution, you want to cut off the first few thousands of accepted parameter values. These values were accepted during the burn-in period. This is because our criteria in the first iteration was set to a very large initial value. The initial value J last, for example here, was set to 9 million. The purpose is to get the ball rolling so that you can find that the updated J last after each round is getting smaller and smaller, which means we're getting closer to the global minimum mismatch. This figure is showing the parameter posterior distribution by using the observation data from the spruce site. We can see several parameters, including SLA, VC max, tall leaf, tall root, tall fine liter, and several others are well constrained by combining the observation data of carbon fluxes and the carbon pool sizes. And then in this figure, we can see that observation data versus the model results, they match pretty well after simulating both data streams. Model is giving a reasonably well prediction. Here are some conclusions from practice 2. We found that sensitive parameters are more likely to be constrained by data. And instead of one value, the data model fusion gave a distribution of parameter values, allowing to display the range of uncertainty caused by parameters. With data assimilation, we could quantify uncertainties and partition into different sources of error and process variability. Tomorrow, we will be practicing on adding and reducing the number of observation datasets and also the parameters for data model fusion. Thanks for watching today's video and have a good day.